Good morning and a very warm welcome to all of you. This is the second workshop for school students. This is called 1%. This is part of our ongoing effort to engage with all at all level the mathematical community in Chennai. As a premier research institution, we feel that it is our duty also to contribute to the mathematics education in the city and maybe at a greater level as well. So the last year we just called it workshop for school students. This year it has been given a name, 1%. This is to allude to the famous quote that genius is 1% and what is that? Yeah, it's already written there. Genius is 1% inspiration, 99% perspiration. Before I hand over the mic to introduce a speaker for today's talks, let me request you all to kindly switch off your mobile so that the lecture can progress without interruption. Okay.
Before introducing the first speaker, I just want to remind you of a few things. First of all, welcome. Put mobile phones in silent mode. Better still, switch them off. Eatables are not allowed inside the auditorium. Free lunch, snacks and beverages are served during the breaks. They are meant to be enjoyed no less than the talks. About the quiz, its purpose is to get you to pay attention to the talks. It's not meant to grade you, so please don't be tense, relax. It is open notes and based on the talks. Listen attentively and take notes. Get your doubts cleared by asking questions. By all means, stop. I don't think any of the speakers will mind if you stop them and ask them a question. About the title itself, as Paramesh just said, genius is 1% inspiration and 99% perspiration. This is attributed to Edison. The workshop is an attempt to provide a bit of inspiration. For any inspiration to be effective, it must be backed up by 99% perspiration, which means hard term over the long term, not just today, not just tomorrow, but over the years. Okay, with this, it's my pleasure to introduce our first speaker of the morning, Professor Vijay Kodiyalam of the Institute of Mathematical Sciences. He did his schooling in Hyderabad from Hyderabad Public School. Then he got his BTech degree in computer science from IIT Madras. Then got a PhD in mathematics at Purdue University, USA. And he was a postdoctoral, he held a postdoctoral position at University of Kansas before coming back to India, and he's been on the faculty of the Institute of Mathematical Sciences, this institute, ever since he came back. It's a pleasure to introduce Vijay.
On my own behalf and on behalf of my colleagues, let me welcome you all again to the Institute of Mathematical Sciences. I hope you have a very interesting day ahead of you. I've read somewhere that it's an ancient Chinese curse which says, "May you live in interesting times." I don't know why it is a curse. I hope it won't be a curse to you all. So let me begin. So the plan of my talk roughly is as follows. I've divided it into 3 parts. So in the first part of the talk, we will do some geometry. So the first part of my talk will deal with the geometry of rotations in 3-dimensional space. The second part is going to be algebra, and there we will discuss a number system called the number system of quaternions. And the third part of the talk is an attempt to connect these two. What is the relation between the geometry of rotations and the algebra of quaternions? So that is the rough plan for the talk. So let me begin with rotations. Now in order to do this, I need to do some experiments. Now we don't do too many experiments in mathematics, although now many schools do have mathematics labs and things like that. We still don't do too many experiments in mathematics. However, some of the greatest mathematicians, the way that mathematical results are discovered is often by working out large number of examples, seeing what is common to the examples and trying to generalize from the examples into some theorem or something like that. So it's all based on experimentation, although when you see the final result, we just do proofs or formulas without much emphasis on what went on into discovering that result originally. So for the purpose of the experiments today, I am going to do two very simple experiments. So I want to begin with this cube. So you all know what this is. This is a Rubik's cube, but for the purposes of my talk, it's not going to be a Rubik's cube. This is just a cube. Okay, it's just a cube, and its faces, 6 faces, are colored in 6 different colors. And what I'll do is I would like to hold this cube in something that I'll call the standard orientation. Standard orientation is I'll hold it like this. So let me draw a picture of this cube here and then explain this orientation, what I mean by orientation. So that's a cube. The cube has 6 faces, right? And we will call these faces, give these faces names. So the face that is facing you, I'll call the front face. So this is the front face, there is a back face, there's an up face, a down face, and then there's left and right. I'll do it according to you. So this one will be the right face and this one will be the left face. So as you are visualizing it, right, left, up, down, front and back. So let me just write this here. So this is front, this face, the square here, this one here is right, this is up, and then there are the other three. There is the back face, the left face and the down face. Okay. And as I said, this, as you can see, this cube is colored, each face with a different color. So in the standard position, which I'll always hold the cube in standard position like this. So in the standard position, this is how the cube looks. So here is front, right, up, back, left and down. So in standard position, the front face is white, the top is blue, up is blue and right is red. So white, right is red and up is blue. Now once I specify these, the others are specified. So if you look at this cube, opposite the white face you have the yellow face, so the back must be yellow, and opposite the red face you have the orange face, so the left must be orange, and down face is opposite the blue face, it's green. This is what I will mean by standard position of the cube. So this is how the cube is initially. Now the experiments I am going to do are going to involve rotating this cube in various ways and seeing what happens. So how I am going to rotate is, how am I going to specify a rotation? So in order to specify a rotation, you need to specify an axis of rotation and an angle by which you rotate, right? So there is an axis and an angle. So to be more precise, what I will do is I will take a coordinate system, a 3-dimensional coordinate system whose origin is at the center of this cube. So imagine a 3D coordinate system whose origin is at the center of the cube, the x-axis coming out towards you, the y-axis going to the, which side is that, right, and the z-axis going right up, right. So here is how it looks. So the x-axis is coming out towards you, y-axis this way, and the z-axis going up. and the origin is in between. So, as I said, to specify a rotation you have to specify an axis and you have to specify an angle of rotation. So, here is what I am going to do. What I will do is I will hold the cube in standard position and do two rotations to it. The first rotation will be a 90-degree rotation around the x axis. Now, when I say a 90-degree rotation around the x axis, that is a little bit ambiguous, right. So, is it 90 degrees clockwise, is it 90 degrees counterclockwise. So, there are two possible meanings it could have and these lead to different answers. So, one has to be careful. So, what we will always mean is I will specify not just an axis, I will specify a direction. I will say positive x axis and 90 degrees. Even then we will have to understand, does it mean counterclockwise or clockwise, and if you must have come across in physics the right hand rule, right, for which various currents, when currents go which direction is the magnetic field, kinds of things like this. So, it is given by the right hand rule. So, that is what I am going to use. When I say 90 degrees around the positive x axis, so here is the cube, the x axis points this way and so I turn the cube like this, right. So, keep this in mind. So, let me write that here. So, rotations will be specified using the right hand rule. Okay. So, I am going to do the first part of my first experiment. First part of the first experiment is 90 degrees around the positive x axis. So, now I have turned it and this is the new position of the cube. Now, I will write down what is the new position of the cube. So, in the new position of the cube, blue is on the left, green is on the right. So, blue is on the left, sorry. So, green is on the right, blue is on the left. Up is red, of course, so then down will be orange. Actually, I need not specify this, right. Once I know up is red, I know the other half. So, I need not specify that, I will not do that anymore. So, up is red and what is in front? Front nothing happened, the white face is still in front because I made a rotation of 90 degrees like this. So, it is still white. Okay. So, now I have got to this new position. Now, what I do is I make a 90 degree turn about the z axis. So, here is the z axis going up and I make a 90 degree turn, I turn it like this. And now, see what happens, the blue is towards you, blue is front, up is red and right is white. So, blue is front, up is red and right is white. So, this is the new position of the cube. Now, what is remarkable about this is the following. Initially, you had white, red and blue and still you have white, red and blue, but in different positions. And the amazing thing is that you can do these two rotations, the effect of these two rotations you can achieve by one single rotation. So, here is my original position of the cube, right, original position of the cube, white in front, blue above, red on the right. So, if I do this, if I take this axis, the axis which goes through this diagonal of the cube, the main diagonal of this cube and then turn it, what you come up with exactly that position. And how much did I turn? I turned this by 120 degrees, right. This is 120, another 120 and another 120, of course, I will come back to the original position. So, what we see is that the net effect of these two rotations by 90 degrees, one around the positive x axis, one around the positive z axis, is the same as one rotation of 120 degrees about this peculiar axis which goes through the main diagonal of the cube, right. So, let us just write that. So, two rotations one of 90 degrees about x axis and another of 90 degrees about the z axis is equivalent to single rotation of 120 degrees about a I'll just say a diagonal axis without specifying what. That's what I just explained, which diagonal axis. Okay, so this is, I finished my first experiment, right. So these two rotations were equivalent to one rotation here. Now I want to do another one, very similar. This very similar one, what I'll do is I'll again start with the cube in standard position. The first part of the experiment will still be the same, namely I'll rotate by 90 degrees around the x axis. In the second part of the experiment, I'll change it slightly. I won't do 90 about the z axis, but 180 about the z axis. So this way and this way. And now let me see the new position of the cube. Yellow in front, red on top, blue on the right. Yellow in front, blue on the right, and red on top. Okay, so this is the new position of the cube. Now we can ask, is this new position also obtainable by a single rotation from the original cube, right? The original cube was white in front, right? White in front and blue on top. This is the original position of the cube, and again it turns out that you can obtain it by a single rotation. What you do is you take an axis through the midpoint of this side and this side, that is an axis which looks like this, an axis which goes through like this through the midpoint of this side and this side, and then I will rotate, and then again you see that you get yellow, blue and red. So again these two rotations are also equivalent to doing one single rotation. So now this should lead you to ask the following questions. Okay, so let me ask, based on these two simple experiments, let me ask the following question. So here's question 1. Is the result of two successive rotations always given by some other rotation. So when I do one rotation around some axis followed by one rotation around some other axis, some different angles or same angles, whatever, is that answer, the final answer, is it equivalent to always some other rotation? That is one question. This is not obvious at all. It is not clear that if you do one rotation followed by another, the result is the same as one rotation. Okay, that is one thing. And so let me, I am not going to keep you in suspense. The answer is just yes. The answer is yes to this. It's not so, it's not very easy to prove. It's not exceedingly difficult also, but it's not very easy to prove that this is indeed the case. The result of one rotation followed by another is indeed equal to some other rotation. And then we can ask question 2, given that the answer is yes, how can we determine the angle and the axis of rotation of the result rotation from the angle and axis of the initial ones. This is my second question. Now this is, if you think about it, the second question is doesn't seem quite easy to answer. So let's see why it doesn't seem easy to answer. In my first experiment, the two axes that I took were x axis, positive x axis and positive z axis. and the final axis turned out to be some angle, some axis through the diagonal, main diagonal of the cube. In the second experiment also I took the x axis and the z axis, but this time the axis, the final axis of the rotation turned out to be some 45 degree, the axis through these two, right. So, it is not even true that if you know the axis of the first rotation and the axis of the second rotation, that you would be able to say in some meaningful way what the axis of the final rotation is, and in fact you can't. It is not determined just by the axis, as we have seen. Just the axis of the two rotations that you do does not determine the axis of the final rotation. So, this is not something about just vectors. You can think of an axis as a vector, right. So, you might be able to tempted to guess that if you have one vector and another vector, you are trying to produce a third vector, the axis of the final rotation from your first two. But this is not just a vector thing, because the final axis does not depend on just the initial axis, it also depends on the angle in some fashion, we do not know what fashion. So, what we would like to answer is how would you determine this, and this is the thing that leads to the system of numbers called quaternions. So, I use numbers in some in some generalized sense, as we will see. Okay. So, yes. Okay. So, it turns out that there is a system of numbers called the quaternions in such a way that some things called unit quaternions, a special set of them called the unit quaternions, correspond exactly to rotations. So, I am trying to say that every rotation can be represented by a number not in the sense that we usually understand it, not a rational number or a real number or even a complex number. This number is called a quaternion, right. So, rotations can be represented by quaternions, and it turns out that doing one rotation after another corresponds to multiplication of the two quaternions. So, you can easily, if you know how to multiply quaternions and if you know how rotations correspond to quaternions, then you will be able to use this multiplication of quaternions in order to find out the result of two successive rotations. You will be able to calculate what is the axis of the final rotation, what is the angle of the final rotation, and how we are going to do it is what I am going to explain now. But before I get into that, let us do one more small little experiment, third one. Here is the cube, and here is its standard position, white in front, blue on top and red on the right. Okay. So, initially what we did was we rotated it about the x axis and then about the z axis and then got to this position, right, that is what we did. Now, I will change this slightly, I will do it in the opposite order, right. So, first what I do is I will take it in standard position, rotate about the z axis and then rotate about the x axis, and clearly you see that the position that you get is not the same as what you got before, right. Doing the rotations in an opposite order, if you change the order of the rotations, then it changes the final position. So, now the axis of this one is going to be a different axis and the angle is still going to be 120, but the axis is certainly going to be a different axis if you think about it a bit carefully. So, how does that tie in with what I said earlier? I said earlier that somehow we should represent rotations by some numbers that we call quaternions, and such that when you do two rotations one after another, that is called the composition of rotations. When you compose two rotations, that should correspond to multiplication of quaternions. But if that is the case, then these numbers certainly have a very strange property, and that strange property is when you do two rotations one after another, the answers are different. So, that means when you multiply these two numbers in one order or in the other order, the answers are different. So, this is a law that is not familiar in the context of our usual numbers, but it should be familiar to you in the context of matrices. So, you know that if you multiply two matrices, then it depends on say 2 cross 2 matrices. If you take two 2 cross 2 matrices and multiply, then the answer depends on whether you do AB or whether you do BA. These two will not give you the same answer. So, the numbers that we are searching for will have this property, will have the property that if you multiply them one way or you multiply them the other way, then the answers are going to be different. So, these numbers do not obey the commutative law, right. Commutative law is a very fundamental law. You have been studying this from maybe 6th standard onwards. You will be told this is the commutative law, this is the associative law, but it is not, unless you see what is not commutative, the commutative law will not make much sense, right. Everything if you have seen is commutative, then the law does not make much sense. You have to see examples of numbers where they do not commute, and that is the example that we are going to see today. Okay. Yeah. So what are quaternions? Now, quaternions are well, they are an example of a mathematical concept for which there is a definite birth date, right. Quaternions have this birth date. So, quaternions birthday is the 16th of October 1843. This is one of the rare things in mathematics where you can actually assign a date to the birth of this concept. So, it is about 170 years old now, right. So, the Irish mathematician William Hamilton was trying to answer the following question. So, surely you are familiar with complex numbers, right. So, complex numbers are numbers of the form x plus yi, where x and y are real numbers, and you know how to multiply them, how to add them. You can do various operations on complex numbers. But when you think of them as x plus yi, you can also think of them as points in the plane. So, here is the plane, and you can think of the point x y. You can think of that point x y as the complex number x plus I y, and then you know addition is given by the parallelogram law, for example, if you think of it this geometrically. So, in essence what was done with the complex numbers is the plane was turned into a number system, and the complex numbers obey all the usual laws of numbers. They are commutative, associative, there is an additive identity, there is a multiplicative identity, everything has an additive inverse, all non-zero things have a multiplicative inverse. All these usual laws are obeyed by the complex numbers. So, once you have done it for two-dimensional thing, that is the plane, it is natural to wonder whether can you do this for three-dimensional space. Can you turn R3, that is our usual space, into a number system which obeys all the usual laws, right. And it turns out that you cannot do this. It is not very easy to prove, but you cannot do it. Turns out that you cannot do this. At that time it was not known, of course. So, Hamilton was trying to solve this problem, how to turn R3 into a nice number system. How do you multiply vectors in such a way that all usual laws hold? Now, you might have done dot and cross product of vectors. So, these fail on different counts. Dot product of vectors is not a vector. So, that's gone. Cross product of vectors is a vector, but it does not satisfy, for example, associativity, right. So, that is a very fundamental property that one would like to have. So, these are not the answer, and it turns out that there is no answer. You cannot do this for R3. But what Hamilton found on 16th October 1843, while he was walking, he suddenly realized that while you cannot do this in 3 space, you can do this in R4. You can do this in 4-dimensional space. If you take in 4-dimensional space, it is possible to turn it into a number system which obeys most of the properties that usual numbers obey, except for this one. The interesting one is it is not commutative. Except that it is not commutative, every other property of usual numbers like real numbers or rational numbers, everything else this thing obeys. And he was so happy apparently with this discovery that he took out his penknife and he was going over a bridge. On one of the stones paving the bridge, he carved this formula. So, what did he carve? So, let us write that down and then try to see what it means. So, he carved this formula. Okay. So, what does this mean? I square equals j square equals k squared equals ijk equals minus 1. What is this supposed to mean, and why was he happy about this discovery? Okay. So, again ijk are surely familiar to you. If you have done a little bit of vectors, then you know that there are unit vectors in the x direction, y direction and the z direction. These are normally denoted by I, j and k. So, these are the unit vectors. But let us forget vectors, let us think of I, j, k as just symbols for now. So, I, j, k are 3 symbols and they obey these rules. I squared equals j squared equals k squared equals I, j, k equals minus 1. Other than this, in the back of his head he had another rule in mind which he did not write down, and that is that I, j and j I are negatives of each other, right. I, j is I, if I, j is okay. So, from this you can deduce. So, from here I will just write down. So, deduce along with, you need a little bit more. Let us say, let me put it that. You can deduce that I j is k is minus j I, that is what I wrote down. J k is I equals minus k j, and k I is j is minus I k. Now, these multiplication rules look a little bit odd. I times j, as I said, they do not commute. So, I times j and j times I are not equal, right. I times j is k, but j times I will be minus k, right. So, they do not commute. And how do you remember these rules? It is fairly easy to remember. Here is a little picture. Right. So, you go along this circle to get the multiplication rule. If you go up, if you go this side, it is positive. If you go the other way, it is negative. That means I j is k, j k is I, k I is j, and that is these 3 rules. And if you go in the opposite direction, k j is minus I k is minus j, and similarly, right, these 3. So, depending, so that is supposed to be a mnemonic for you to remember the rules of multiplication. Okay. So, this is what he wrote down. And so, what are quaternions now? Now, quaternions are like complex numbers. Complex numbers, as I said, are x plus yi, right, where x and y are real numbers. Quaternions are like that, except that they have, instead of 2 components, they have 4 components. It is in 4-dimensional space. They represent points in 4-dimensional space, and they are written like this. So, a quaternion is a number w plus xi plus yj plus zk, where w, x, y, z are all real numbers, usual numbers that we are familiar with. For complex numbers, you will just have w plus xi, right, 2 things. But for quaternions, you have w plus xi plus yj plus zk. So, what do I mean by saying it is a number? When I say it is a number, what I mean is there are definite rules for adding, multiplying, and these rules obey the usual rules of addition and multiplication that numbers obey, with the significant exception of the commutative law. Except for the commutative law, other laws are satisfied. So, what are the rules for addition and multiplication? If I have one quaternion like this and I have another quaternion, how do you add? You just add the w part separately, the x part separately, y part separately, and z part separately. For example, if I have 2 plus 3i plus 4j, and when I do not write a k, that means 0k, right, no k, plus 2i minus j plus k. So, you just add separately 2, and there is no no real part there, so I just leave that. Here's 3i and 2i, 5i. Here is 4j minus j, and no k here and 1k there. This is how you add. Addition is very straightforward, right? You just add the things separately. And as for multiplication, that is what this table is supposed to do. These two things together will help you multiply. So, if you want to multiply 2 plus I into 3 plus j, say, you multiply as usual. Since all the usual laws hold, you can use the associative law, right, and multiply. So, 2 into 3, 6, 2 into j, 2j, 3 into I, 3i, and I into j, ij. Ij, as we said, is k. So, the answer is 6 plus 3i plus 2j plus k. If you write it as first the constant part, then the I part, j part, k part, then you will have to interchange those two and write it as 6 plus 3i plus 2j plus k. So, this is how you add quaternions and you multiply quaternions. Now, I am saying that all the usual rules are satisfied. So, for example, one of the rules, one of the important ones is that non-zero numbers have a multiplicative inverse, right. So, if you take a real number or a complex number, if it is not 0, then it has a multiplicative inverse. So, what about that? Do quaternions also have multiplicative inverses? It turns out they do. Okay. So, if you take the quaternion a plus bi plus cj plus dk, I want to say that non-zero quaternions have an inverse. So, what does it mean to be 0? When is this equal to 0? We will say that this is 0 if all of those numbers are 0. If a is 0, b is 0, c is 0 and d is 0. If all of them are 0, then that is the 0 quaternion, otherwise it is not the 0 quaternion. So, for a plus bi plus cj plus dk, which is not 0, there is a multiplicative inverse, which is, okay, to see what that which is let us go back to complex numbers. Complex numbers, if you take a plus bi, so that has a multiplicative, if a and b are not both 0, then it has a multiplicative inverse. So, what is the multiplicative inverse of a plus bi? A minus bi over a squared plus b squared, right. So, a plus bi, for the complex number a plus bi, the inverse is a minus bi by a squared plus b squared, which is the same as saying a by a squared plus b squared minus b by a squared plus b squared I, right. That is that you know, for complex numbers that is the inverse. For quaternions also a very similar thing holds. So, the multiplicative inverse of this happens to be a minus bi minus cj minus dk by a squared plus b squared plus c squared plus d squared. Very similar to the thing for complex numbers. Now, since the quaternion is not 0, we know that not all of a, b, c, d are 0, and so this quantity here is not 0. A, B, C, D are all real numbers, so their squares are all non-negative, and if this has to be 0, then all of them have to be 0. But we started with a non-zero quaternion, so non-zero quaternions will always have this as the inverse. How do you know this is the inverse? You have to check. You have to multiply this with this and see, using the rules for multiplication, you will see that you will get 1 as the answer. That involves quite some effort, right. It's lengthy to write down, but easy to do. Once you know the rules, you can multiply. Okay. So, the reason I am mentioning reciprocals is because we need reciprocals for our description of rotations. Okay. Now, one more thing about quaternions that I probably should mention is the following. Yes. So, in the complex numbers, suppose you want the square root of minus 1. So, what is the square root of minus 1? I and minus I. So, square root of minus 1 has I or minus I, that is plus or minus I. So, there are 2 square roots of minus 1 in the complex numbers. Are there any others? Is there any other complex number whose square is minus 1? The answer is no, and it has to be seen, right. You need to see this. You need to show that I and minus I are the only 2 complex numbers whose square is minus 1. By contrast, in the quaternions, Hamilton did a very interesting thing. What Hamilton did was, he put in 1 square root of minus 1 for every direction in 3 space. So, here is a little proposition. I am not going to prove this. So, AI plus Bj plus Ck squared is minus 1 whenever A squared plus B squared plus C squared is 1. For every direction in 3 space, a unit vector is represented by AI plus Bj plus Ck, where A squared plus B squared plus C squared is 1, right. That is a unit vector in some direction in 3 space. For every direction in 3 space, he has given you 1 square root of minus 1. If you square it using the rules and see what the answer is, it will exactly be A squared plus B squared plus C squared. All the other, there will not be an I term, there will not be a j term, there will not be a k term, everything will cancel. We will be left only with A squared plus B squared plus C squared, minus of A squared plus B squared plus C squared, sorry. So, if this is equal to 1, then the final answer will be minus 1. So, this is one of the interesting properties of quaternions. There are infinitely many square roots of minus 1 within the system of quaternions. Okay. So, that finishes 2 parts of my talk. We have dealt with rotations and we have dealt with quaternions. Now, we will deal with the third part. The third part is, what is the connection? So, what is the connection between rotations, which are some geometric things, and quaternions, which is some algebraic number system which we have defined in this manner. Okay. So, in order to see that, I will make one definition. Again, I will do this by analogy with the complex numbers. So, I said complex numbers you can think of as points in the plane. So, here is the plane. And every point in this plane is an xy. I will think of as a complex number x plus yi. Now, I want to look at those complex at the picture in the plane, which is the unit circle, the circle with center at the origin and radius equal to 1. So, here is the unit circle. Now, that does not look very good, but it is okay. So, think of it as the circle with center 0 and radius 1. So, all of these also are complex numbers, of course, right. That is a complex number, that is a complex number, that is a complex number. All of these are complex numbers. These are all x plus iy, x plus yi or iy, whatever, however you want to write it. Now, what is common to all of these complex numbers? The modulus is 1. That means x squared plus y squared is 1. And that, of course, you know, is the equation of a circle with center 0, radius 1, right. The modulus is 1. Similarly, I want to consider unit quaternions. By unit quaternion, this number is called the modulus of the quaternion. Just like x squared plus y squared is the modulus of the complex number, the number a squared plus b squared plus c squared plus d square That's not, that's the square of the modulus, right? It's the square of the modulus of that quaternion. Now, I want to consider all quaternions whose modulus is 1. So, let us consider, we will define this unit quaternion. A unit quaternion is an A plus Bi plus Cj plus Dk, where A squared plus B squared plus C squared plus D squared is 1. Okay. Now, this has some very interesting geometry behind it. Okay. So, what is the interesting geometry? Here you see circle, you get a circle, x squared plus y squared equals 1 is a circle in 2-dimensional space, right. In 3-dimensional space, if you consider x squared plus y squared plus z squared equals 1, so what do you get? You get a sphere. Similarly, one would expect in 4-dimensional space, which where the coordinates are a, b, c, d, say, instead of x, y, z, w. If you consider all points where a squared plus b squared plus c squared plus d squared is 1, that is going to be a higher dimensional analog of the circle, sphere, and the higher dimensional analog, right, the 3 sphere, it is called the 3 sphere. So, the unit quaternions are actually points which lie on the 3 sphere, just like the unit complex numbers are points that lie on this circle, the unit quaternions all lie on this 3 sphere which lies in 4-dimensional space. Now, it is hard to imagine 4-dimensional space, of course, I can't imagine it, and most people can't, I am sure. It is difficult to imagine 4-dimensional space, but nevertheless we can study a lot about it by analogy. From 3 and 2 dimensions we can guess lots of things that might be true in 4-dimensional space. We will think of 4-dimensional space just simply as 4 tuples of numbers, right, and this the unit quaternions somehow as a higher dimensional analog of the sphere S2 in 3-dimensional space, this is S3 in 4-dimensional space. So, I will just write that down. So, these form a 3 sphere in 4-dimensional space. Okay. So, those are the unit quaternions. It is what I am going to use to describe rotations. So, now let me tell you how to associate for every rotation one unit quaternion. Okay. So, associate a unit quaternion to every rotation. So, let me mention some things about rotations here. Now, all the rotations I did were around axis which went through the origin, right. All rotations of the cube that I did in my experiments were through axis which went through the origin of the coordinate system. Now, that is what I am going to restrict myself to. I am not going to consider rotations about points other than the origin, right. We are only going to consider rotations around axis which go through the origin of the coordinate system. So, once you have a rotation which goes through the origin of the coordinate system, what is needed to specify it? As I said, there is an axis that is needed, right, and an angle of rotation. So, you need 2 things to specify a rotation, an axis and an angle. So, let us take a picture in 3-dimensional coordinate system here. Suppose that is the axis of rotation, some axis. Now, this axis is going to be a unit vector. You could take a unit vector in that direction in 3-dimensional space. So, that is a vector, you could just take a unit vector in that direction. This is a vector of length 1 in that direction, right, and call this vector of length 1 something, right. So, let us call this, so this vector, so unit vector in the axis direction. So, let us call this, let us say u for now. So, u will be a combination of the 3 basic unit vectors I, j and k, right. All unit vectors, all vectors are combinations of I, j, k. In particular, this unit vector will be some a I plus b j plus c k, where a square plus b square plus c square happens to be 1, right. So, this is a unit vector in axis direction u. So, we want to associate a unit quaternion to every rotation. So, for theta around the axis u, associate this quaternion, cos of theta by 2 plus sin of theta by 2 u. Okay. That might, if that looks abstract, we will do examples right now. Next thing. Okay. So, what does that mean? I am just, what I am doing here is giving you one quaternion for every rotation, and I am telling you how to get this quaternion. It is a unit quaternion defined like so. So, let us do it. So, first for our first experiment with the cube, we began with the positive x axis, that is the one that points towards you, and then made a 90-degree rotation around the positive x axis. So, let us see what is the quaternion associated to that. So, for a 90-degree rotation, around the positive x axis, the associated quaternion is the following. So, what should you do? Theta is 90 degrees and u is just the positive x axis, means it is just I, right. U is just going to be I, the unit vector I, and theta is 90 degrees. So, theta by 2 is 45, cos of theta by 2, sin of theta by 2 are both 1 over square root 2. So, the quaternion is 1 over root 2 plus 1 over root 2 I. That is the quaternion. Similarly, what is it for the, so in the second part of the experiment, we rotated about the z axis for 90 degrees. So, similarly, for 90-degree rotation, about the positive z axis, the associated quaternion (1 by root 2) plus 1 by root 2 k now. The unit vector in the z axis direction is k. So, this is how you get a quaternion, unit quaternion from a rotation. Okay. So, now what is the theorem? So, this is the really remarkable theorem. I will not be able to prove any part of it, I will state it though. So, this theorem is going to tell you what happens to a point in 3-dimensional space when you perform a rotation. Okay. So, let P be a point in 3 space. I am going to represent this P as a quaternion, right. So, a 3 space point will have an x coordinate, y coordinate and z coordinate. So, let us say P x y z. So, represent as a quaternion. I will call that quaternion little p, and what is the quaternion? It is very easy, xi plus yj plus zk. This quaternion does not have a constant term, right. A general quaternion will have a w and then xi, yj, zk. This has no w, w is 0. So, represent a point as a quaternion and let q be the quaternion associated to a rotation. So, I have told you how to associate a quaternion to a rotation. So, every rotation will have some quaternion. Now, I want to know what happens to the point P when I do this rotation q, and that is what this theorem answers. Then consider Q, P, Q inverse. Q inverse is just the reciprocal quaternion, right? Now all of these are quaternions. P is a quaternion, little p is a quaternion, Q is the quaternion associated to a rotation, Q inverse is the reciprocal. Then consider Q, P, Q inverse. This is still in 3 space. What do I mean by this is still in 3 space? 3 space is just things consisting of something I plus something j plus something k with no w part, right? No w part. I am saying that if you take something which has no w part and multiply by q on this side and q inverse on that side, the result still has no w part, right? It is still in 3 space and represents the image of P under rotation, appropriate rotation. Okay. I do not have time to do one example for this, but I want, because I want to do something else. So, something else that I want to do is the following. So, why is this useful? Why is this theorem so useful? The theorem is very, in fact it is very useful in most of the computer games. For example, when you see a scenery that is shifting, right. So, if you are trying to maneuver your aircraft or whatever around a shifting scenery, it is quaternions that are actually used in order to implement all the rotations that are needed. So, you are changing your position, you are rotating, your view is rotating, all of these are in fact implemented by quaternions. So, this is useful, but let me tell you why it is useful mathematically. The reason it is useful mathematically is the following. See, if you can compose 2 rotations by simply multiplying quaternions. So, if I wanted to compose these 2 rotations, if I first want to do x axis and then z axis, it turns out that you will have to multiply in the opposite order. So, you have to first, so you take 1 by root 2 plus 1 by root 2 k and multiply with 1 by root 2 plus 1 by root 2 I and compute. Just calculate this out. Now, I am not going to do the calculation, I will just write down the answer. Turns out that this is half plus half I plus half j plus half k. So, what does that do for you? What that does for you is the following. This is also a unit quaternion. This is the one unit quaternion and another unit quaternion. By the way, that is another remarkable thing I should have said. The product of 2 unit quaternions is again a unit quaternion, and that is related to the fact that when you multiply 2 sums of 4 squares, you also get an answer which is the sum of 4 squares. Anyway, never mind. So, do this calculation. This is the answer that you get. And this answer can be written in the following form. You can write this as cos 60 plus sin 60 into 1 by root 3 I plus 1 by root 3 j plus 1 by root 3 k. This is just, you can check that this is correct. So, what is this telling you? What this is telling you is that these 2 rotations one after the other, if you do, it is equal to a 120 degree rotation. Remember, this is theta by 2, right. In the quaternion formula, did I hope I did that, yeah. So, in the quaternion formula you have a theta by 2 there. So, this is 120 degree rotation about this axis, and this axis is exactly the axis which goes through that main diagonal of the cube, right. So, it tells you what the answer, you can use this to actually predict results of rotations. Okay. I have only 2 minutes left. So, in these 2 minutes I would like to show you one video. This video is an interesting thing. It was, so in the formula for a rotation there is this theta by 2. Why is there a theta by 2 as opposed to a theta? So, this question was actually considered by Dirac, and Dirac gave a very nice experiment in order to illustrate this. So, what he said was something like the following. You take this cube here, take this cube and you connect, assume this room is also cubical, right, assume the room is also cubical, you connect this corner to that corner, that corner to that corner, connect all the 8 corners of the cube to the 8 corners of the room by elastic strings, right, strings, you connect them with strings which can stretch. Then what you do is you turn the cube, so let us say in standard position it looks like this, you turn it 360 degrees. When you turn it 360 degrees, all the strings will get tangled, right? Turn it a further 360 degrees. So the tangling becomes worse, right? So you have turned the cube 720 degrees around this axis, say z axis, and all the strings are tangled. Now what Dirac showed was the following. It is possible to untangle everything, keeping this cube fixed without changing anything about this cube. It is possible to untangle all the strings by just moving them around and under and over and things like that. It is possible to untangle. It seems very hard to believe at first sight, and unfortunately I do not have a video which shows this, but Dirac phrased it in the form of an experiment involving a belt. This is called the Dirac belt experiment, and that is what is shown in this video. It is a 2-minute video.
Illustrate graphically an elusive property of the spin of the electron. In quantum mechanics, all particles are connected to each other and to every observer in the universe. For an electron, there is a quantum state or wave function relative to a given observer. If this observer should walk around the electron, making a full turn of 360 degrees, then the wave function changes sign. This means that while a quantum mechanical system involving electrons is not brought back into exact coincidence with itself after it is rotated by 360 degrees, it is brought back into coincidence with itself after it is rotated by 720 degrees. Here is Dirac's visual metaphor performed as the Philippine wine dance. Watch closely how the dancer winds the cup through 360 degrees, acquiring a twist in her arm. Then she winds the cup through another 360 degrees, and the twist in her arm has disappeared. Notice how the ribbon is moving around the inner sphere. The ends of the ribbon do not move. They are fixed to the respective spheres, and yet now the ribbon returns to its original position and all the twist is gone. This is the Dirac string trick in modern form. We have programmed the computer to twist the space between the spheres. The strings, whether one or many, are located in that space and acquire their twist from the twist of the space. Once we untwist the space, the strings untwist as well, and we have given you a glimpse of quantum mechanical reality.
Yeah, so I just have one comment to finish. So you saw this Philippine wine dance or something. You're going to go and have tea now. Kindly do not experiment with the teacups and saucers that way. I'll stop with that. Thank you. Any questions? Thanks.